Welcome students, we are back with another lesson. In this lesson we'll discuss Einstein's photoelectric effect. So Einstein used Planck's quantum theory to explain the photoelectric effect in the year 1905, for which he received a Nobel Prize in the year 1921 for his contribution in theoretical physics and his explanation for the photoelectric effect. So according to Einstein's, the light travels as a discrete photon. Fine. So can you see this individual packet? This individual packet is known as your photon. This individual packet is your energy packet. Okay, you can assume it like a particle. So this is your photon, which is your energy packet. This photon exhibits your particle nature as well as your wave nature, which we'll discuss in more details in our upcoming classes. For now, you can only consider this as your energy packet. Fine. This can shows the particle nature just like your ball. Okay. Similarly, it can also shows the wave nature. So these photons are always found in discrete quantities. By discrete quantities, I mean they are found in 1, 2, 3 and so on. You will never find half photon or 1/3 photon. You will always find one complete photon. Okay, that's why they are called discrete. Right? Now, if this photon has a frequency mu, okay, fine, then the energy of the individual photon can be written as E equals to h time nu, where h is your Planck's constant. Fine. And this mu is the frequency of light. Okay, so up till now what we have discussed, that according to Einstein, the light travels as a discrete photon. This photon is a energy packet which exhibits your particle nature as well as your wave nature. If this photon has a frequency mu, then the energy of photon is given, the energy of individual photon is given as h nu. Fine. So some of the main points of the Einstein's photoelectric effect are given here. Now the first point states that the photoelectric emission is the result of the interaction of two particles. One photon of incident radiation and the other an electron of the photosensitive material. So consider you have a photosensitive material. So the first point of the photoelectric effect states that the photoelectric effect takes place when you have a photon, this is your photon, which interacts with the electron of the photosensitive material. When this photon goes and strike this electron, okay, so photoelectric effect is the interaction of these two particles only. Next point, the free electrons are bounded within the metal due to the restraining forces on the surface. The minimum energy required to liberate an electron from the metal surface is called the work function of the metal. So inside this photosensitive material, these electrons are bounded to the surface. Okay, they stay on the surface of the photosensitive material because of the Coulombic attraction between the electrons. Okay, there is a Coulombic force taking place into the picture, and there are various other types of forces. Okay, for now you can just consider your Coulombic forces. One of the forces are Coulombic force. So this electron is attached to the surface by some force. Fine. Now the energy required to remove this electron from this photosensitive material, okay, to liberate this electron, to free this electron from this material, This energy required is known as work function of the material, which is denoted by W naught. So if you supply an amount of energy of how much? W naught, the electron will be emitted from this photosensitive material. Now, point number 3, each photon interacts with one electron. Now again consider you have a photosensitive material on the surface of which you have free electrons. Now when the light is incident, then each photon interacts with one individual electron. Fine. So if there are how many photons? 1, 2, 3, 4 photons. Then they will interact with 1 electron, 2 electron, 3 electron and 4 electron and so on. So each photon interacts with 1 electron. And the energy h mu of the incident photon is used up in two parts. The first part of the energy is used in liberating electrons from the metal surface, which is equal to the work function of the metal. The remaining part of the photoelectron is used in imparting the kinetic energy to the ejected electron. So consider a photon which interacts with this electron. Now this photon has the energy h nu. Fine. Now what will happen to this energy? So some part of its energy will be consumed by this electron to free the electron from this surface. The consumed energy, the energy which is taken by this photosensitive material, is known as your work function, which is represented by W naught, and the rest of the energy will be taken by this electron as a kinetic energy, which is half mv max square. Fine. By conservation of energy, the energy of the incident photon should be equals to the energy absorbed by this photosensitive material to emit this electron, which is your work function, plus the remaining energy which this photoelectron takes with itself, which is half mv max square, which is the maximum kinetic energy of the photoelectron. So the energy of the incident photon is h nu equals to the work function W naught plus the maximum kinetic energy of the photoelectron, which is half mv max square. Now I can send this work function to the other side of the equation. Then I can write half mv max square equals to your h nu, and if I send W naught to the other side, then it will be minus W naught here. So this is the expression for the maximum kinetic energy of the ejected electron. So K max equals to half mv max square, which can also be written as h mu minus W naught. Now assume if this radiation is of threshold frequency mu naught. So if you remember, what was your threshold frequency? The frequency below which no emission of electron takes place. In order for the electron to be produced, the frequency of the incident radiation should be greater than your threshold frequency. So now in this figure, if this radiation has the threshold frequency, then its energy will be h mu naught. Fine. Now all of this energy will be absorbed by this photosensitive material, and the ejected electron, okay, this ejected electron, what will happen? Will it have any remaining kinetic energy? No. Why? Because all of the electron is absorbed by this photosensitive material to eject the electron. Fine. So there is no remaining energy which the electron can take with itself. Therefore the kinetic energy equals to 0. Fine. Now if we apply the energy conservation, then the energy of the incident photon is h nu naught equals to the work function, which is same W naught plus the kinetic energy of the photoelectron. In this case, what is the kinetic energy of photoelectron? It is 0. So this term will be neglected. Fine. So your work function equals to h mu naught. Fine. If the incident photon is of threshold frequency mu naught, then its energy h nu naught is just sufficient to free the electron from the metal surface and does not give any kinetic energy. This is the one which we have just discussed. So in this case, what happens? Your incident energy h nu naught equals to your work function, which is written here, h nu naught equals to your work function W naught. So if I substitute this in my equation 1, then I can write this equation 1 as the maximum kinetic energy of the ejected photoelectron, half mv max square, is equals to h mu. Instead of W naught, I'll write h mu naught. So h mu minus h mu naught. From here I can take this h expression, I can take this h common. So h multiplied by mu minus mu naught. Fine. Let's give this equation a number. So equation 1 and your equation 2, these two equations are known as your Einstein's photoelectric equation. Fine. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I'll re-explain it to you again. And in our next class, the dual nature of matter, your de Broglie or your de Broglie relation. Fine. So again, thank you.